Detectors. As name says, it is a semiconductor device which can be implicated to detect the photon presence. Such a device are known as a photodetectors. They transform optical signals into the electrical signals. So that we call it as a photodetectors. When excess electrons and holes are generated in a semiconductor, so in response of that, power and current will be generated. That depends upon the intensity of the light which falls on a particular p and n junction. So this photodiode is made of a p layer and a n layer. In between we have a intrinsic region. That's why it's called as a pin detectors, PIN detectors. Where why we are using this a true intrinsic material here is, as we know, in intrinsic material the free charge carriers are 0. There is no free charge carriers. Either we can use a pure intrinsic material or we can use a high resistivity material also. Then the mode of operation, in which region it will operate. As you can see here, when a p and n region, that is in a reverse bias, that is a third quadrant, it will operate. So here this current, when we are not incidenting any light on a particular p and n junction, that current which is flowing over here, that we call it as a dark current. Why it is a dark current? Because we are not incidenting any light on a particular p and n junction. So this current we call it as a dark current. So when we apply the light energy on a particular p and n junction, what happens? Because of the drift velocity, that is a diffusion velocity, what happens? The electrons will drift back to their respective region. So the current which is flowing, that is a reverse current. So that current equal it as a G1. So this is the intensity of a light at G1. So if we keep on increasing the intensity of the light, then the reverse current which flow in a p and n junction is, it keep on increases. So why it is increasing? When we incident a light on a particular p and n junction, electron hole pair will be generated, and because of the electric field intensity, so they will swept back to their p region and electron will swept back to the n region. So this, from this VI characteristics, what we can say, an electron hole pair will operate at the third quadrant of region. So that is a photodetector working, that will work on third quadrant. So that's based on the quadrant operation. If we connect the power supply, that is negative terminal is connected to positive and a positive terminal is connected to the negative. So along with this, one load is connected. So current which is flowing from the positive terminal, and that current is a IR current, reverse bias current. So this is about the construction of a PN pin detectors. So here, as you can see from the figure, that is the width of the P region and the width of the N region and the width of this intrinsic material region. Which one is larger? The intrinsic material region is larger. Why it is larger? That we will get to know at the end of this particular topic. And why this P and N region is lesser is because when a light falls on the particular region, it has to cover the entire intrinsic region. So for that reason, the P and N region is made, the length is made lesser compared to the intrinsic material region. The same graph, the same circuit, here it is oriented, the oriented circuit of the previous circuit. The same P region, intrinsic material region, and N region which is connected to the reverse bias through this resistor, and N region is connected to the positive polarity, that is nothing but it's a reverse bias operation. The same circuit we are oriented form, that we tilted here. So as this is a photodiode, a light has to incident on the particular region. So the construction is like this. So when a light of energy h nu So the Planck's constant and the wavelength of the particular light energy falls on the particular P region. So what happens, that we have to see here. The width of the I region is larger, that will affect again the current production by this particular photodiode. So for that reason we are increasing the length of I, and the P and N region width is lesser. So this is about the construction details of a photodetectors. Now we see the working operation of this particular photodetector. So as you can see here, the energy graph of the particular P and N junction. So this one is a reverse bias. So that's why you already studied this one, energy graph of a particular P and N junction. When at equilibrium, the Fermi level will be the same for N region as well as the P region. When it is forward bias, the Fermi level will shift upwards, and when it is reverse bias, the Fermi level for the N region will shift below. So it will shift below by the time of Q times the applied reverse voltage, that is Q into VR times it will shift below because of the reverse voltage. So this energy band graph, the basic we already know. Now what happens? So consider the energy band graph of a reverse bias region. So this is our P region and this is our N region. This is the depletion layer which is between the P and N region, and this is an intrinsic material. So that itself acts like a transition layer, that is a depletion layer. So what happens when a light falls on a P region? So as you can see here, the light is directly incidenting on the P region. So P is taking the light at the beginning itself. So that's a construction. So when a particular light falls on the P region, see here, so this is our P region. So first we discuss about here three conditions we have to consider. So when a light falls on a P region, what happens? When particular light energy falls on a N region, what happens? And when it comes to the depletion region, what will happen to the working? So when a light falls on a particular N region, so here H nu, so that is represented over here, H nu, that is the energy of the light that falls on a particular P region. What happens? An electron hole pair will be generated. So here, so this is a hole and this is the electron. What happens when a light energy falls on a particular P region? What happens? Electron hole pair will be generated. So this is the hole and this is the electron hole pair will be generated. So where exactly the hole will be there? Hole will be present at the valence band, electrons will be present at the conduction band. So electron hole pair will be generated. So when electron hole pair is generated, what happens? The electrons which is present in the conduction band of the P region, what will happen? It will move around. So it will move around in the P region, and when it comes to this particular junction, so what happens? So the diffusion of electrons will takes place. So when it exactly comes to the I region, that is the intrinsic material, that is the depletion region, the diffusion of electrons will takes place. So when it enters this region, what happens? Because of the electric field will be present here, no, in a depletion region. So this is the electric field. Because of this electric field, the drifting of electron will takes place and it will come back to the N region. Getting my point? What happens? So if this is a P and N region, that we studied over here, so because of the positive as well as the negative ion, the electric field will be present, that we know. So because of that electric field, here the drifting of electron will takes place. So when a light energy falls on the P region, electron hole pair will be generated. So hole will remain in the valence band itself. What happens to the electron? Because the whole parent region is a P region, but this electron in the conduction band is present in the P region, and when it move around over here, what happens? When it comes to this particular junction, what happens because of this electric field, it will come back to the N region. So this is the electron place which is present, which come back to the N region. So this is the process at when light falls on the P region. So when the same light falls on the N region, what will happen? So consider this as a light energy. When this light energy falls on this N region, again the same thing, hole and electrons will be generated. As electron which is present in the N region itself, it won't do anything. But the hole which is present over here, no, it will move around over here, and when it comes to this junction, particular junction, what happens? Because of this electric field, it will drift back to its original region, that is a P region. So the electron will come back to this region. So this process we call it as a hole diffusion. Now what happens? Hole diffusion is taking place in N region and electron diffusion is taking place in P region. Understanding my point, what I am telling? So when a light falls on the particular P region or a N region, EHPs are generated and they will move around. So because of the electric field, the electron, if it is the electron, it will come back to N region, and if it is a hole, it will come back to the P region, so that they are coming back to their original region. So this process we call it, that is occurring in the P region, is a electron diffusion, and the hole that will move around and it will go back to the P region, that process we call it as a hole diffusion, that takes place in particular N region. So this is about the P and N region. The same thing now. So when electron, that is a light energy, falls on particular depletion region, what happens? So when a light energy falls on this particular depletion region, again the same thing, hole and electron pair will be generated. Because of this electric field, what happens? The electron will drift back to the N region and a hole will drift back to the P region. So understanding this point, so what happens? Electron hole pair will be generated and they will move back to the, if it is electron, it will move back to the N region. If it is a hole, it will go back to the P region. Similarly, in case of a depletion region also, if it is electron, it will drift back to the N region, and if it is a hole, it will drift back to the P region. Why? Because of that electric field which is present in the depletion region. So this is about this energy band graph that you have to explain in your own words. So now, photo generated carrier, the key points, the photo generated carriers as well as the photo carriers. What process is happening over here when a light falls on the particular P, N and I region? So the carriers are generated, energy carriers are generated. So that carriers, we call it as a photo generated carriers as well as a photo carriers. So both, with the both name we can call, we are generating the charge carriers, so that we call it as a photo generated carriers or a photo carriers. Next one is a photo current. So if a current starts to flow, when we connect it to external circuit, the current will starts to flow because of the light falls on the particular P, N and I region, pin region. So that current production, because of this process, we call it as a photo current. So these are the two terminologies that we have to explain. One is a photo generated carriers and the second one is a photo current. Next one. And terminologies with respect to this particular photodiode. The first terminology or first parameter is quantum efficiency. So this is the symbol for the quantum efficiency symbol into Q. So that is nothing but a quantum efficiency. The quantum efficiency is the ratio of number of carriers generated per unit area per second to the number of photons shining on the surface of photodetector per unit area per second. So that is the efficiency. So here quantum efficiency is nothing but a ratio of carriers which are generated by this process in a pin junction region to that of the light which falls on the particular region. So the entire whatever the light energy which falls on a particular pin region, it won't be converted into a carriers. So that is explained over here. Quantum efficiency. So that quantum efficiency in equation that can be represented as a JOP. Here this is a JOP by Q divided by POP by H nu, where JOP is nothing but a optical current density, and a POP. So capital P and small subscript you have to use POP, that is nothing but a optical power density. The maximum value of this quantum efficiency, that is it's a unity. The maximum value that it can reach is unity. So this theory, along with this equation, you have to mention what is JOP and what is POP. So that we have to mention, where Q is a charge and h nu is the light energy. And the maximum value that can reach in here is 1. That is about the first parameter, which is quantum efficiency. The second parameter is ADP. So ADP is nothing but a avalanche photodiodes. ADP is nothing but a avalanche photodiodes. So to detect a light of low intensity, what it says, why this ADP is coming over here. So in a previous case, that is a quantum efficiency, so all light which falls on a particular PN junction, it won't be converted into carriers. So the sum of the when light falls on a particular PN junction, we are not saying it as a constant light energy is falling on a particular PN junction. It may vary. So if we want to detect the light intensity of, that is a low intensity light, then that type of detectors we call it as a avalanche photodiodes. That is avalanche photodiodes. So what happens here is, in order to detect the light energy of low intensity, we need to operate this PN junction in such a way that avalanche multiplication should occur. Avalanche breakdown we already studied, where what happens, EHPs are generated and a charge carrier starts increasing. The same process here. The light intensity, so whatever it falls on here, so that the generated photocarrier results in significant changes in the current intensity. So here avalanche multiplication will takes place, same as avalanche breakdown. So this type of, if we operate the particular PNN junction, so that it can multiply the generated light intensity in such a way that a lower light intensity can also be utilized in generation of a charge carriers. So that type of detectors we call it as avalanche photodiodes. So the theory you have to write, that is about ADP and how it is going to operate. ADP and its process. Next one is, the first one is a quantum efficiency and the second one is about ADP, that is APD, avalanche photodiodes, APD, and the third one is a response time. So response time is nothing but a fast photodetector could respond to change in incident light. How this photodetector will respond to that incident light, so that we call it as a response time. How fast it will respond to particular fault light, so that time we call it as a response time. So here, in order to this is a parameter, one parameter to measure the photodetectors. In order to find whether a photodetector is a slow responding photodetector or a fast responding photodetector, then it depends upon the three parameters. The first one is diffusion time, and the second one is transist time, and third one is diffusion, that is the depletion capacitance. The three parameters. So here the diffusion time is nothing but a time it will take during the diffusion of electron as well as a hole. So where exactly the electron diffusion takes place? Electron diffusion is taking place in the P region, and hole diffusion is taking place in N region. So if in order to have a higher value, that is in order to have this response time as low as possible, what should be the P and N width should be very less. The first parameter is diffusion time. So how I can reduce my diffusion time in order to reduce my response time? That can be reduced by making the P and N region as thin as possible. So that is about first condition, diffusion time. And the second one is a transist time. So transist time is nothing but the time, transition region, depletion region, both are same. The transistor time is nothing but time here in between the depletion region. So that is what the drifting of electron and hole, it will takes place over here, no? That we call it as a transition time. So again, this transition time depends on what? So this transition time depends upon the width. So the W, because transition is exactly happening in the transition region. This is our transition region. And the capacitance, C depletion. So when you can see the capacitance, so capacitance, that is a two parallel plates separated by the depletion layer. If P acts like a one plate and N acts like another plate, and this depletion region acts like a dielectric media, then this capacitance we call it as a depletion capacitance. So this capacitance as well as the transist time depends upon what? Depends upon this value of W, that is nothing but a that is a depth of this intrinsic material. Now, what will happen if capacitance is small? Again, one more formula, that is capacitance formula we know, that is area into epsilon divided by distance. So the capacitance will increase if the distance is less. Capacitance value will increase if the distance, that is a depletion width, if it is less, means the capacitance value will be more. Again, that capacitance, why we are taking that capacitance here to explain this response time is because of this tau constant. Tau is equals to RC. Because of this time constant, that again depends upon the value of capacitor C, we are considering the depletion capacitance. Now what will happen? The first parameter, that is a transistor time as well as a depletion time. You can see here, by increasing the value of the, that is if width is small, what will happen to the transist time, and if a width is large, what happens to the transist time? Transist time will occur in the depletion region. If this is a P and N region, so this depletion region we call it as a transition region. So if this width is small, means what happens to the transist time? That is also small. The electron or a hole which is present, it has to move back to its original region, means if the length is small, means the time required for that process is also small, that is also less. If the width is large, then also the transist time is also large. Understanding my point? This is about the depletion region. If the width is less, then the electron which has to go back to its original region and the hole which is go back to its P region will be less. If the width is large, means it has to travel long distance. Then depletion capacitance. If this width is larger, for smaller case we are explaining, if this width is small, that is if this capacitance D in the denominator, if this capacitor, that is if denominator is small, that is this width is small, means the capacitance value increases. If this capacitance value increases, the time constant tau will also increase. So that is what it is explained over here, capacitance will increase. If the width is large, in the sense denominator part is increasing, means the capacitance value will decrease. That is what is explained over here. And also the absorption rate. This absorption rate depends upon the width also, how it will absorb the light energy. If the width is small, then absorption rate is less. If the width is large, then absorption rate is more. So from this what we can say, if the width is larger, then transist time is more as well as the capacitance value is less, as well as the absorption rate is more. So here advantage is more when width is large compared to the smaller width of the depletion region. For that reason, as here the absorption rate is more, for that reason we are making the depletion width, that is the intrinsic material width, as a larger compared to the P and N region, that you can see from here. Why the width of the P region is smaller and why the width of the I region is larger? Because absorption rate is more. So this is about the response time. The next parameter is spectrum range. So spectrum range, again we already discussed about this one. If the light which is falling on a particular P and N junction, if a light which is falling on this particular P and N junction, so how much will be the value of this light? It should be greater than the value of Eg, then only the electron hole pair will be generated. That is explained over here. If this H nu is less than the Eg, then what happens? EHPs are not generated, because the light which is incident on the particular region, it has to cross the energy gap, then only EHPs will be generated. That is nothing but a spectrum range. Next one is a detector responsivity. Detector responsivity is nothing but a ratio of a photocurrent to the incident optical power. This is one ratio that we have to remember, IL by PE. That is a photocurrent which is produced by this process to the incident optical power, PE. So this completes photo detectors.